guys, welcome back. So today was a little bit different. I sat down and wrote a library that kind of has no purpose, but it's really there just to demonstrate how you could build your own libraries in PlayBASIC, and in particular I compile them to DLLs using PlayBASIC to DLL. And this library is like a recreation of the internal shape commands, which is not very useful, but it shows things like managing a bunch of vertices, because each shape has a bunch of vertices, points in space, if that term is confusing too, and the shapes are defined with a bunch of edges. Now all it does is just renders these things out on screen. This is the thread about it on the forum. We'll fire up PlayBASIC. Now, because we're talking about building DLLs, that PB2DLL is partnered with 164P. I think there's like 4 revisions of it. So the last revision of 164P. So you'll need that version, which is what I've got loaded here. We'll go to open up the examples, and I'll show you the master library. This is all just PlayBASIC. Nothing special about this at all. So we've got a project. We've got the main document. Just got our little test in it, and the shapes library itself. Now this has a similar form that I tend to use when I make libraries. Mostly it's for my own sanity later on. I find it helpful if I try and have some dates in there and at least some sort of identifier that tells me that when this thing was updated, what functions are in this thing, which I've put these ones at the top here. So we've got a little emulation's got things like you can create new 2D shape. I'll have to rename the function names because otherwise they'll clash with the internal ones, of course. Create 2D shape, delete shape. So the shape has these resources have a life cycle. We can create a resource and then delete it, which is important if you're going to make libraries that third parties will use. In this case, we need a draw function to draw this thing onto the screen. We've got to think for scaling the shape, rotating the shape, and setting the vertices, and reading the vertices back, and setting the edges. And that's pretty much all of the commands we've created. If we step through it, we've got a bunch of gobbledygook, and I hope people are following me with this. But maybe we'll go back to the example first. So we run this program here. This is all just regular PlayBASIC 164. We'll run it. It shows you our shapes being constructed. It's drawn to the screen. We'll hit space. We can get an animated version of that. So we're seeing about 500 shapes being rotated, scaled, and drawn to the screen. Now all this is just regular PB code. This is not compiled yet. This is an older build of PB as well. It's 164P. Revision 4, by the looks of that. Now, once we compile this, we don't need to include all of this code here anymore. We just include the DLL. Now, I've already done this for us. So I'll just flip out this one here. I'll load the other project where that's already been done. Test shape 2D library, that's the one. This project's got 2 versions of the test in it. And it's just one file. This include file here is generated by PlayBASIC to DLL when we compile something. And it's really just a list of function declarations. Let's have a look at, if we open it up, we'll see it makes a header for us by default. Makes a link DLL statement with the DLL name in it. And then that's the function names that appear in this DLL, which is all the functions we want to expose to our user. In this case, it's just us, So there's no other code, because all that code's compiled in the machine code inside the DLL. I can close up that page so we don't need it. If we run it, we get an idea of difference in performance. So it runs pretty nicely. I don't know how many line fragments we're drawing, but it's a lot. I mean, we haven't really done anything to make this optimal. That's the key point. If I hit space, I go to another test. Our version of shapes doesn't even try to clip. They're just drawn regardless if they're on screen or not. And if you're familiar with drawing lines, line clipping is a bit of a pain in the backside. So it works pretty good. But the process of this is what trips people up, I guess. Let's go back to our actual library itself. Now, the way I build these things, and we have to work with how the tool works. So if we want a function to be exportable to our DLL, all of this code here will be built into a DLL regardless of what it's called. But the only functions we'll be able to see and call are the ones that have this DLL underscore at their head. Now, when we're working with this from PB, notice how I've got two files in this project. I've got the main file, and this becomes my test area. I'm just calling these functions as normal to try to make sure that these things behave the way I want them to behave from PB normally. Because if they don't work the way you want them to work here, compiling it to a DLL is not going to fix that. But it does mean that when we're doing this testing, we're going to use the full DLL name here. Eventually, when it's compiled, these names are ripped off during that process. This example here makes a shape, checks the status of the shape, just to check if that function even works. We set a bunch of vertices in sort of a ring form. So odd numbered vertices are at a radius of 100, and odd numbered vertices are at a radius of 150. So we're just putting that, we're calling our vertex shape thing here to position our vertice. Then we're reading them back to make sure we can set our vertex and we can read it back correctly, trying to make sure we've got no general or basic sort of errors in our library. We're setting our edges of our shape. All this works pretty much the same as what the internal shape commands work. That's why I've sort of chose to do this example pretty much. We draw the thing onto the screen and make sure we're drawing what we expect. And the demo I think it's all it's using here is just the rotate, the scale, and the draw function. The rest of it's just PB code, fooling around, changing the size of the shape and the angle to make it a bit more interesting to look at. If we run this example again, so in this setup screen here, it's got some vertices we've plotted out. We've read them back to make sure we're reading them back, and I'm drawing them offset from each other so I can check they're actually working properly. Then we've got the shape drawn as just line fragments, just normal PB line commands, by the way, nothing special. So all this is just a whole bunch of PB line commands. I don't know how many there are actually. I guess we can work it out. So yeah, number of edges. Yeah, number of edges. This is the number of used edges. The other one was, well, yeah. So here we're drawing 500 of these things by that. So I'll just go print. It's an approximate, really, of how many lines we're drawing. So we'll go number of edges times max, I think it was, for the number of lines. Cut it off. Don't know. Right. So, not sure if you can see that or not, but we've got 35,500. So that's a lot of line fragments for PB to draw without having an optimized line drawing routine. Because every line fragment's being clipped to the viewport. Keep that in mind. Internal shape commands don't have that. They don't use the PB line command at all. They use their own line functions. Alright, so in this case here, our primary example here is a two-file example where I'm writing my library in one file, which is this shape, 2DShapes.pba file, it's self-contained, so it doesn't require any functions outside of this or any declarations outside of this, none of that. It's all, if I just cut away this stuff here and just comment this all out, we should compile it and nothing happens. That's the beauty of a library. That's what we'll refer to as a library. So if we run it again, nothing. Boom. So it has no main loop, none of that stuff there. In the setup code, we've very minimal code actually in our library. We've just got some declarations at the top of it. A 2D vertex is floats. Shape edge has a status to check whether we want to draw that edge or not. Starting vertex, the ending vertex, and then a type structure to represent our each shape. So each shape has its own vertex count, its own edge count, its angle of rotation, a status to check whether we need to actually rotate the vertices before it's drawn or not. Sometimes you may need to, sometimes you may not. A scale, of course, and a couple of buffers here that deal with storing the vertex data. This might be a subject that people have, find confusing, but we're just talking about poking data into a bank, and we're using a typed pointer to do so. If we look at the create shape, I've documented some of this stuff, and hopefully you can sort of follow through, pick through the example a bit yourself. But so when we create a shape, we're just checking if that shape index already exists. If it does, we delete it. It's a bit rough as guts, but it'll do for the demo. Now we allocate a new shape type for this location within our array. And we grab a typed pointer. And I've called this pointer me because it's kind of short and it's easy to remember pretty much. And we're conceptually thinking about that from here on in, we're referring to this shapes.index structure within this array directly. We're bypassing this array completely and pointing directly at these fields. So I can store the number of vertex in it, the angle, the status, the scale, whatever other stuff I want to store within it. Below here, we're creating some banks to store vertex data. And we're doing that by just a regular PB bank. This function asks for the number of these items we want to store and how many bytes each one of these things will take. So it just multiplies the two together and allocates a bank. If we check it out, I've named it something that the user wouldn't want to call anyway. It's an ugly name. In my world, that refers to like a private function in PB. So this allocate bank function, we're just checking the count is something that's legal. The structure size is like a legal size to make sure before we allocate something that makes no sense. Allocating a bank of 0 bytes makes no sense. So the size of this thing, we're allocating a new bank, but its size is just count times the structure size. To refresh our memory, if we're getting a vertex, we're storing the number of these vertex plus the size of a type vector. This is this structure at the top up here. This thing here. So it's 2 floats packed together. In byte terms, that's 8 bytes. Since they're 32 bits each float. This structure here would be 12 bytes. They're 3 integers. So we've got status as an integer, start vertex, end vertex. This structure here is what? 1, 2, 3, 4, 5, whatever it is. I don't know. Probably about 20 bytes long. So if we use the size of, we can get the number of bytes this structure has. And that's better. It's better for your code in general to use that approach. So you never have a baked in numbers down here. I could type 8 down here and this still works. But if I ever change this structure here and I make it bigger or smaller, that breaks the rest of the code. That's why we use these little helpers. And this is not done at runtime, by the way. Size of is computed during compilation. It just substitutes this for however many bytes that structure is. Now, since it's a bank and we've allocated a bank, I want to get a pointer straight to it, and then never have to call get bank pointer all the time. So I know the index of the bank, I know the pointer to it, and I can just use those things as we move on. The way this little library works is we have a vertice buffer that's non-rotated, that's the original vertex, and we can have a second buffer that's for rotated vertices, and the edge buffer down here. All the same principle. When we delete something, we're going to make sure we go through and release these banks that we've used in this case. Like if you're making a library that deals with sprites in a create, you have like your own kind of custom high-level sprite functions. And let's say they allocate sprites, then in here, in your management code, you're going to have, it's going to remember what sprites you're using. When you delete your super sprite or whatever you're going to call it, you're going to delete those sprites with it as well, so that they're not leaked out into the system. It's your responsibility to clean up after yourself, pretty much, is what I'm saying. So I'll let you dig through the library yourself. It's kind of a lot to take in. Let's have a look at how we actually build this stuff. So this is our test code. We've got 2 files in it. Hit F5 to check it still works the way we expect. Looks pretty good, it's working the way I expect. Hit the button to quit out of it. If I go back to the folder, I've got a link to PB2DLL already. It's not installed in this folder, but the same principle. To set this up, if you're not sure, when you first run it, it doesn't know where PB is. And you might have more than one version of PB on your system. That's perfectly legal to do, by the way, because I have like 3 or 4 different versions all the time. If that's the case, you would go to Settings, select Compiler, click the Locate button, and then guide it to wherever your install location is. Most people would install it to their Programs folder, which is like the default location for where the installer chooses. But you can put it anywhere you like. I mean, who cares? Once it's installed, you can just copy that folder somewhere else. That's how I have multiple versions, by the way. Nonetheless, so what you would do to build this thing, since I've already, you go to Convert File. In this case, we'll just pick this 2DShapes file, because we're only compiling one file out of the project. We can't compile projects. That's a key point, key distinction that's worth making. Let's give us a bit of spiel about what it's doing. It's loaded the file, it's compiled that file using that version of PlayBASIC you pointed this thing at. So PB2DLL calls the PlayBASIC compiler with your code, source code, the shapes.pba code in this example. It produces a bytecode representation of that. Then PB2DLL loads that bytecode into memory, generates an assembly representation of this thing. Then it calls flat assembler to build the DLL. So there's a bunch of steps going on, and it only took 4 seconds. But it also builds our link file, which is the go back into here. This is the master library example. So it builds this include here. It puts this link DLL include in front of it, really just to try and avoid collisions with other files that might be in the system or within your project. And it's built this thing here for us, so we can just pull this code here into our project, and now we can call these functions as if they were part of PB. And effectively, they pretty much are. And they're stored in this DLL here. Now, these DLLs are very small because when we use internal functions in PB, it's calling back into PB to do those things. So in this example here, when we call draw a line, where's this draw function? Wherever it is anyway. we're calling line C, which is a coloured line. It's better to call this version than to call line, because line is always going to be polling the current ink colour. This way we can just we can read the current ink colour once and then just call this version, and we never have to do anything to it. But in the DLL, it doesn't have a version of this code, this draw line code. It just calls back into PB's internal libraries to do this for you. That's why the PB2DLL tool and the version of the compiler have to match perfectly. If they don't, things won't work properly. If you find old examples on the boards that are built with old versions of PB2DLL, you probably have to recompile them yourself. So they probably won't work with whatever the last build of 164P is. Oh wow, it's always so complicated to explain this stuff to people, but really it's not that difficult. You know, the process is as I just showed. You know, once you've written your library of code, that's the important thing, is writing that library, making sure that you give your functions the appropriate names. Once you do that, you just load the thing up and sit back and wait for it, and that's done. In this case here, what I have to do is I've got to copy then these two files, the DLL and the include file, into my example project over here. So I've already done this for us anyway. So we've got the DLL library there and its little include file. This is our example function, example before. The beauty of this is that you can build libraries that plug into your application. As your applications get bigger, the problem with most basics is that you can't modularize. You can't actually pre-build a slab of it that you're not working on all the time and just include it in a compiled state all the time. So being able to build a DLL out of something, we get high performance out of that code from the get-go, and we don't have to have this big wad of source code kludging up our project. Like, imagine if your project is, you know, in this case here I've got 2 files, but a lot of games you see with a lot of bigger projects, you see people writing might have 10 different files and a bunch of include files to boot. You know, over time, it's a lot of code for PB to keep building every single time you hit F5 to run or click the run button up here. In this particular case, this example runs pretty well just in standard PB. Alright, so one last time with the compiled version of our little, what do you call this, globule? I don't know. Looks like those lanterns you see at, not sure where they are. Yeah, it's kind of cute. But not bad for drawing 35,000 lines straight to the background buffer. The second demo there. I don't know how many lines that's drawing. A fair few. The internal shapes library does things like it keeps track of where the vertices are. So when you scale and rotate these things, it can work out, do a clip against the viewport to reject drawing something if it's off screen. So if I move these objects over here, all of the objects outside of the screen bounds are still being processed and drawn, even though the fragments are not on screen. Alrighty, I hope this helps someone. I hope this is not all in vain, and I hope people can wrap their heads around building ways of expanding their PB experience in general. You know, some other projects have been written in this in particular. Some of the tools around here, libraries like the OpenGL tool, were written in PB2DLL, so it's not really a toy. You can do some interesting stuff in it if you care to put the time in. But you know, it's not simple for people, I guess, and it doesn't take any prisoners. So if you don't quite understand something, and you might find it'll crash in some circumstances. I found today that when I was writing this DLL, that it was crashing on one function when I exported the code, and that was because I had a return value that was incorrectly typed. I'd cut and pasted this set shape function and this get shape function. I'd cut and pasted from it. I left this result after here. Now what this means in PB land is we're returning a floating point variable from within this function here called result. In the wonderful land of machine code, what you might not realize is that the CPU and FPU are actually different parts of the chip. They have different registers. They're effectively two different chips stuck in a box. When we deal with floating point, we have got to pop the results off. In functions, we normally have this mentality where the result of any sort of function that does a floating point operation is left sitting on the FPU, and then the caller is meant to grab this thing off the FPU. If we do that here in PB, and then we have a function that's exporting a floating point value, and we don't clean it up when we call this thing, it'll crash. And it took me a little while to work out what the hell was going on. I was like, oh gee, that's annoying. It's not working straight away. But you know, them's the breaks. I also found another thing too with function names. If I see with get 2D shape angle, if I put it like a hash on here, the PB2DLL tool doesn't remove this hash when it generates the name on the export. And while it's legal to have a function name in PB with a hash in it, it isn't in Windows in particular. And it'll get stripped off. So even though we're just trying to export this DLL name, it's being exported, but the names don't match, and it couldn't find the name at runtime. And yeah, it was all kind of annoying there for a second. Just make sure I've removed that. Get shape scale. Okay, vertex is all right. So there are things that you need to be careful of when you're doing with this stuff. If you head over here, I've linked to the blog actually, and the blog is a very long document. I don't expect people to run through and read this stuff in one sitting, but I do have an expectation that you'll pick through this stuff and try and get your head around how this process works. You'll find examples tucked away in here too. Initially, it's just talking about what we're supporting, what we're not supporting. Over time, we're supporting pretty much everything. Yeah, flexor, some rotator stuff there. I say pretty much everything because you can't do everything on the DLL side. As an example of drawing 1 million rotated vertices in PB, which is just mental, to be honest. Absolutely mental. But you can do it. I mean, that's how much number crunching you actually have. Now, we're not using things like SIMD or these kind of AVX functions of your CPU at all. This is just good old school, good old fashioned floating point. The stuff that's been around since the 486 days, or the early Pentium days, I should say. Anyway, my point is this function has a lot of stuff in it, well worth your time. Keep track of what's in these history files, if you find problems with it, I mean, we might be able to fix some of them, but my time's pretty limited, so the ones I saw today, I'll definitely try and get those fixed if I can get my office set up. But again, time is a wonderful thing. For now, I hope to get someone over the line, get someone started, get someone enthusiastic about doing this stuff. In terms of number crunching, you can do, like you can render whole screens of dots at high frame rates, you know. And the more you understand what you're doing, the better you can craft code that's going to pretty much give you a result that's more like, that's approaching C results rather than just, you know, your average interpreted BASIC out there, which there are a lot of them. Alrighty, that'll have to do me. Thanks for indulging me. Thanks for listening to this garbage. Hopefully you learned something from it. Hope if you haven't, that's okay. Just keep, you know, chipping away at it. I'm sure you'll pick it up. And we'll try and make this thing simpler in the future, but this is how it works today. Thanks. Bye.